for a little bit late that there's some internet issue. But what I'm trying to do is I want to connect remotely to the EC2 server. I try to show you how to launch an instance. And before I get started, does anyone successfully install, follow this, use AWS instance instructions to install on your AWS account? So how do we launch it? So you see now I have 0 running instance and 0 volume, etc. So what you do is you click the launch instance button. And here, the first step, we search the Ubuntu. So the first one, the 18.04, will be the one you should select. So that will be your army. And now there are a bunch of instances. Maybe most of them I don't have the limit, but I do have this now for one. So I select that, and the next step, configure the instance detail. And we do not need to change anything here. And add storage, be sure you add enough storage, maybe 100. It won't cost you that much. I will just set 64 for now, add storage. And add tags, probably don't change anything. Security group, we just select the existing one, the default one, which everyone should have one. And so ignore that, you will just launch. So it will ask you to use existing key pairs or create a new key pairs. So this key will be used for you to access the remote servers. So if you don't have one, you can create a new one, but I already have one. So I will just acknowledge and launch my instance. So you see now the instance are launching. It's a green checked, which means you can use it. So when you click it, you will go back to your EC2 dashboard. And you will see your public DSN, your private DSN. Be sure do not leak it to others. It will be bad for you. And then copy it, how to log into it. So you see that I will open a new terminal that I will log in using this SH2. Yeah, so this step is already being written online within that instructions. So if you scroll down, after you launch the instance, it talks about how to connect the instance. What you do is you copy your instance ID, which is ec2-aws.com ID. Oh, by the way, if you create a new key, trying to make it not public-wise but private-wise it. So just run this command with your case name. And so this is example how do you log in. I believe I'm lack of something. So let me stop it and go back. And I will try to launch my instance here. So you see it's running. Probably will take some time, but it should work. No. That's interesting. Okay, maybe there's still some internet issue that I'm setting up my VPN now. But after you launch it, you should see some green button here, what I'm logging here on the other server. That this is your IP address as what is stated in your EC2 box. Like here, you can see your public DNS, and you log in here. It should be like within your home.ubuntu folder, and you can do a lot of things. Like just follow the instruction from the installing CUDA, installing MXNet, and until the running Jupyter. So it should be good to go. Any question for launching the instance, etc.? Yes? Denied? What instance do you apply for? It's a P2 X large? And you got denied? Wow.
It said that we have received your limit increase request, and there was a.
Was there a reason why they decline you? Do you already have your credit put in your account?
Yes.
Okay.
Is that I'm really sorry, but at this time we are unable to proceed your EC2 limit increase request. Limit are put in place to help you gradually ramp up due to sudden unexpected spike. I don't know.
Okay,
or I must change the zones of resource.
can you try maybe, so do you try P2? Can you try like G2?
G2?
Yes.
Okay.
Or maybe try another instance, see what happens. But let me know if it still doesn't work.
So I need to wait one
Yeah,
day.
one business day
Okay.
is their maximum, but usually it's pretty quick, like 2 or 3 hours.
Okay.
Yeah.
G2, right? G.
Yeah,
request.
G2.
Okay. Thank you.
Okay, since we're kind of running a little bit late, let's just start with, let's just resume with what I have now.
Excuse me?
Oh, yes.
I lose track around the choose AMI section on AWS website.
What?
I'm trying to do the instruction on AWS, and yeah, I think I lose track around this section is choose AMI.
Oh, choose army? Okay.
Yeah.
So you just need to choose this on search Ubuntu in your search box.
Yeah, I did it.
And then
And
you choose the first one.
Okay, the first one.
Yes.
Yeah, and can we just go from there?
Yeah,
one
yes.
more time?
Sure. So you click launch instance again, but definitely this time I will fail because I only have one limit for the instance. So what you do, you search like Ubuntu here. And then you'll find this 18.04, and you will just choose that. Just select it.
Yes, I did it.
Okay, awesome. And then you find the instance you have.
Okay, GPU.
Yes, I will just do a search here. So I do a P2 here. Since I have like an instant limit that I can have one instance here, so you just choose it. And then go to the next step. Add storage.
P2 X large. Okay.
Yes, P2X large. So next.
Yeah, as storage, you can choose 100. I will choose 64 here. Or 100 is fine. As much as possible, especially you're training larger thing, the larger is better. And you add tag, you won't change anything. And for the security group, you select the existing one. So you should have a default security group in your name. Is that okay? Yeah, and then you click review and launch. And you click launch. And then if you don't have a K pair before, you just like create a new pair. For example, put your name there. It's like any name. Does it work? Okay, great. I'm not going to launch it here because it definitely will fail. So let's go back and resume our lectures. So this morning we're talking about a general, like still the general model for convolutional neural net, and I upload a new slides to. Oh, probably I haven't upload yet. So I will do that later. So I changed a little bit on my slides with a new one. So I will upload to my repo later online. But let's talk about a more recent architecture for convolutional neural network. So here is like the overview. I hope I can finish them today. So the first one we're going to talk about is DayNet. DayNet is derived as the first convolutional neural network back 20 years ago by Yang LeCun. And it was trying to get the figures from the handwritten digits. And it is a AT&T project in order to recognize the handwritten digits for like either coastal code or letters, so just numbers from 0 to 9. So what is the data set looking like back in 1990s? It's like only 10 numbers, and we have the 15,000 training data. We are 10,000 of them are testing data, and we have this 10 class, but they're all gray scaled image, so it's not RGB anymore. And each of them are of like 28 by 28 pixel. And then they are synchronous scaled, which is already been cleaned. So let's see a short video. What does it look like back like 20 years ago? So you have this number coming in. Each digit is coming in, and you have this filter on your left-hand side, and they're trying to recognize whether, for example, for the first layer, you're trying to recognize what kind of edge they are, or maybe what kind of noise they are. And then in the upper layer, you're trying to do a little bit more complex convolutional layers, and then it recognizes it as like the number here. You can see it's like 1, 3, 4, pretty accurate here in the answers. Okay. So what does DayNet really look like? It's pretty simple. It contains 2 parts. The first part is called the convolutional block. So it contains like a convolutional layers and the average pooling layers. As you can see, it's like convolutional layers here and average pooling layers here. So for the convolutional layers, it is trying to recognize the spatial patterns for the given image. And it uses a 5x5 kernel and a sigma activation function. And for the average pooling layers, and it will try to reduce the dimensionality. So firstly, we have this 28 by 28, and we use the average pooling, then it will be 14 by 14. And another part are 3 fully connected layers. As you can see, there are dense layer here. Their have size is 120, 84, and also 10 output. The reason we have 10 output is like we have 10 class we need to classify, and they are all probabilities. However, we can feel that if we use dense layer, it's pretty expensive, because if this layer has like 120 units, and the next one has 84, then the width will be 120 times 84 in the total width for just this part, and also we have also a dense width for the other part. So it's pretty expensive for us as both memory and computation. And notebook, talk about later. So DayNet is pretty successful back then, but until 2012, before AlexNet came up, there's no really advanced convolutional neural network. So until 2012, that Jeffrey Hinton's lab, they came out with this 2 GPUs neural network. You can see there's like kind of 2 layers on the top, training on 1 GPU, on the bottom training on another GPU, but they're like pretty parallel with each other and the same architecture. So back to AlexNet, it won the ImageNet competition back in 2012, and it reached amazing error rate, which only 16%. So what's the difference between AlexNet and the traditional machine learning models? As you see on the left-hand side, when the input image comes in, it will be fed using some feature engineering that the researcher do it manually, and then fit in some state-of-art algorithm. Back then it was SVM, and then it was trying to achieve some error rate, but it was stopped at around 25%. Like we say here, it doesn't really work for all the other traditional machine learning algorithm. But for the deep learning, we fit in the convolution neural network. And they lay some feature itself. We don't need really to do some feature engineering ourselves. And we fit soft-max regression in it, and it will just return what class it should be. So what's the difference between AlexNet and DayNet? So first, it's a deeper and a bigger DayNet. As you can see from the previous architecture, it's like 2 GPU trained on it. And the key modification here, we have first Dropout. I will introduce Dropout a little bit later. It is trying to regularize the neural network to keep it from overfitting. And second, we use ReLU for training rather than Sigmod, since ReLU is much faster and it won't suffer from the vanish, a gradient vanish. And also we use max pooling here rather than DayNet. It only use average pooling. So max pooling can try to extract some features or phenomenon features. And so here's a kind of comparison between AlexNet and DayNet. So we have a input image come in. For AlexNet, it's like RGB image, which 3 times 224 by 224. But for DayNet, it's 28 by 28. And that's why we need to fit in a larger kernel, which is 11 by 11 kernel. But previously, it was like 5 by 5 kernel. So like that is for the smaller image, but now we have a bigger image. We also have a larger pooling side because we are trying to extract more feature using this max pooling over larger windows and to try to reduce the dimension. And then we have more layers for AlexNet compared with DayNet. As you can see, we have more output channels. We have 3 additional convolution layers. And that's another reason we are using Dropout here, because we had too many layers contents with each other. Probably they were overfittings to learn the feature. Probably they will just memorize the data themselves for the networks. So for the AlexNet, we have 1,000 class output because the ImageNet computation and it has 1,000 class. But for the DayNet, it only has dense 10 because it only has 10 digits there. They're trying to recognize. And here, as you can see, these 3 output layers. For the AlexNet, we increase it to 4,000, which is super large because it was trained on GPU, rather than DayNet, which is pretty small neural network. So the first trick we do for the AlexNet is we replace the Sigmod activation function to the ReLU activation function. So as I taught yesterday, like the Sigmod is kind of really smoothing function between 0 and 1, but ReLU is kind of straightforward. It's have either 0 as gradient or 1 as gradient. So why we are using that? Because in the next photo, as you can see in the next picture, the gradient for ReLU will be the orange line. And so every time if we are in the app on other smaller than 4, if x smaller than 4 or it's like bigger than 4, the gradient is pretty small. And if the gradient is pretty small, then there will be some problem. Because when we're trying to do the gradient descent and during the back propagation, we times all the gradient together. And if all the gradients are pretty small and we times all those smaller things together, you can say if we have this 0.8 to the power of 100, then it will super small, and probably the computer won't recognize it, and probably it will be vanished to be 0. And we call this phenomenon as gradient vanishing. So which means that the total product of those gradients will vanish in the end. So this is a big issue because our computers suffer from this 16 bits floating points that it won't recognize some digits are smaller than this range or bigger than this range. And also, if your gradient is too small, then probably you won't make some progress during the training, because think about it, if your gradient is too small, no matter how large your learning rate is, every time you still make a small move. And also, it suffer with the bottom layer. Only top layer will be trained, and the bottom layers, the gradient is too small, it won't train themselves. And the second trick we have is we add a dropout layers after 2 hidden dense layers. So why we need a dropout? First, the dropout is trying to have more robustness, rather which is more regulation. So what is dropout? Dropout is like, as you can see in the paragraph here in the middle, which is the traditional MLP with no dropout, with 1 hidden unit. But now, maybe it's not that stable enough. Maybe some of the weights, some of the hidden unit here, they're kind of overfitting already. They memorize data already. So if we remove that weights randomly, and it can still produce the same result, then it means that it will be stable, right? So rather than just rely on maybe 1 or 2 units, if we random remove maybe half of, like 50% of the hidden unit, and the neural network is still working, so which means it's not relying on specific ones, and which means they are stable. So that's the basic idea for dropout. And the formula on the left, so you calculate the hidden unit, you apply the dropout, and you times the weights with the new H, and then you do the softmax on the O. Any question for dropout or before that? Yes, please.
For the convolution layer, is it the kernel, the filter kernel with the static value on the filter, or is it a filter that also adapt itself every time we feed the new training image to the CNN?
So if I understand correctly, you're asking whether we should apply ReLU for some specific kernel?
I'm not sure what is the convolution layer. Is it the filter kernel?
Oh, yeah, right. You're right. So the convolution layer is just what we talked about this morning. It's like those like square, that's those kernel we're trying to slice with, and you apply that kernel as your convolution layers. Exactly.
Yeah. So those layers, they have its own value in each cell of the kernel, right? If I don't understand wrong, and the value of each filter, will it be updated every time it learn the new image or not, or is it constant value?
So what we do is like say there's like weight matrix, which is like you can think about your kernel weights and you time with the input plus your bias, and then you apply this activation function. So the LINAC is trying to apply this signal activation function here, as you can see on the left, the sigma, and then the AlexNet is trying to use in ReLU, which is formula here on the right. The ReLU function, maybe it's not showing here, a little bit slow, but it will just have either 0 gradient or 1 gradient, so it won't vanish, because if you times 1 every time, it still be 1, right?
So
Yes.
you mean each convolution layer, it will adjust or change itself every time we learn the new data set, right?
Yes, after one convolution layer, you will apply the kind of activation, and to the next layer pass it.
Okay, thank you.
Okay, let's resume. After the dropout, by the way, the dropout is only using during the training. We don't want it to be used during the prediction because we want to use everything we have already, right? We don't want to drop out half of the weights that we trained it, which means we waste half of our efforts. That's why we only use on the training to do the regularization. And the third part is the trick of the data augmentation, like the cat, like what we're talking about today. It's like when they trained AlexNet, they did a lot of data augmentation with those image, to crop it, flip it, and do more hue, do more brightness on it. So after notebook, the next neural network we're going to talk about is called VGG. It's pretty powerful, and it's coming from the Oxford University Visual Geometrical Group. That's why it's called VGG. So, what does it look like? So, as we know that AlexNet is like a deeper and a bigger version of DayNet, which have a better performance because it's got deeps and it got width. But if we go even bigger and deeper, then this neural network probably a little bit cumbersome. Can we write more code that we just put them all the layers in the block and just call the block ourselves? So that's the whole idea for VGG. So we can go deeper or go wider. So we can do the 5x5 convolution. It can be like 3x3 convolution. And the VGG block on the left-hand side, you can see it's like include 3x3 convolution, 3x3 convolution with padding 1, and then a max pooling in the end. So this is as the same as part of the AlexNet, but AlexNet, it didn't group this convolution and max pooling to be a block, but VGG just block it, so we can call it later. So we call it as VGG block, which is similar as part of AlexNet. So here I'm going to show the general architecture for the VGG. So you can see on the left-hand side is VGG block. It contains a lot those VGG block and then 3 dense layers after it. So it's pretty similar to the AlexNet on your right-hand side, where like it's like where it's like 2 VGG block here. It's like max pooling, and then still 3 dense layers. So VGG block have different architecture version. You can see there is like VGG 16 and VGG nexting. So what does it mean? 16 means that it has 16 layers. So how do we count the layers? We have like maybe 3 dense layer here, and also for the VGG 16, it means the other 13 layers are convolutional layers. And for VGG 19, it means the other 16 layers are convolutional layers, etc. So it's just like how many layers does it have. So as a summary, we learned 3 architecture already: the LINAC, the AlexNet, the VGG. So DayNet has 2 convolution plus pooling, and it used like 2 hidden dense layers. And AlexNet is kind of a bigger and deeper DayNet. And it used relu, dropout, and pre-processing, like data augmentation, to make the neural network even powerful. And VGG is just like bigger and deeper AlexNet by repeated with this VGG block. So any questions? Nowadays, you mean in the classification or like common public computation? Okay, I will repeat it. So the question is that, do we still use this neural network nowadays?
I mean, like all 3 of them, because it seems to me that all 3 are more like it's developed from by one to another. Yeah, so I'm just curious, like nowadays, do we use only VGG or like the whole thing?
Okay, so probably we don't use any of them now. If you want to do state-of-art research, I will introduce more models later. There are like maybe a million, like 100 models after it. So these are pretty phenomenal models back in that time. So like DayNet is like the first convolutional neural network back in 1990s, and AlexNet is the first one that makes the breakthrough for deep learning. So they're like pretty important neural networks that we should know that what are their ideas, what are their intuitions. So that's why you don't really need to like know how to code them, how much layer do they know, do they account for like those VGG 16 or VGG 19, what are their truly architecture, how many hidden layers in it, but it's just like we want to get the idea.
I see, gotcha.
Yes.
And one last thing, can I say that dropout is more like a way to optimize like unused stuff in the model, something like that?
I mean dropout?
Yeah, dropout.
Yeah,
the process.
dropout is pretty useful if your layer goes deep. So if your layer goes deep and stack with each other, then probably it's overfitting like the traditional machine learning models. And if we drop out, for example, people usually do 0.5, like 50% of the weights, and which means that you drop out like 50% of the union within that layers. And that means that if some of the neurons they're overfitting, we don't need to rely on them. And we just randomly drop out them every time we train it. So like each iteration you train, we drop out randomly. We choose 50% randomly. And we calculate, just use that weights to calculate. Yeah. And the next time when you train, you using maybe another random selected 50% of weights. So that's why how you keep it to be stable. Yeah.
I say thank you.
Yeah. Good question. Any other question? Are people tired now? Okay. So if you're tired, let's look at video. And I'm going to show you guys a video. So this is a Gluon CV that what we can do using the convolutional neural network. A small demo, 3 minutes. Should I play the video? I guess it worked. How about you show it? Can you just like show it? Is it possible? Can you just search for this website? Okay. Sorry, 1 second. You can just search Gluon CV. Yeah, okay, this is much better. This is a small demo that we train using different neural network models, like especially ResNet. That's one of my colleagues' works. They put a camera there in Japan. Yeah, and this is trying to recognize different kinds of cars on the road with some probabilities. And this is like semantic segmentation that on the road, you want to segment different objects. So you see there's trees, there's people, there's cars here. Yeah, and this is the most amazing one. You can do the post estimation. And the inference speed is pretty quick. You can recognize whether it's like a face there. Yeah, sometimes the input quality is not that high, but we can still recognize something. Like the traffic light, like the trunk, like the car. Yeah, that's a road of California, which is pretty dry. You can see like the grass is yellow. Okay, thank you. So there are like lots of like architecture here, mask RNN and ResNet, etc. We are going to talk about later. Hopefully you guys are a little bit excited now. So that's like a Gluon demo. We also have like a Gluon CV like model 2, which has a lot of trained models. So the VGG will reach phenomenal result like outcome back in that years. So for 1,000 sample, it will achieve accuracy about 0.7, which is pretty amazing. Like 1,000 sample per second prediction. So next up, we're going to talk about networks in networks. Remember that we're talking about the last layer. We have like 120 times 84, like dense layers weights, which a lot of parameters. So we call it the curse of the last layers, which is have lots of parameters and the computational really expensive. So the DayNet has like 48K parameters, as we calculate using the CI times CO, which is the input kernel times the output kernel times the kernel size, which is K squared. And XNet has like 26 million. VGG has like 102 million, which is crazy. I don't know how do they train it. So the key idea is like, can we get rid of those fully convolutional layers? Can we use some like new models, probably some more special convolutional layers, like doing pooling and threading to reduce the resolutions? And the answer is yes. First, it's like we want to reduce the resolution progressively with this NIN, network in network. And what do we do? We increase the number of channels, but then we also apply the one-by-one convolution. And we talked about the one-by-one convolution this morning. It's like work as the same as a dense layer. So it's the same functionality, but it has much less weights. So rather than previously, like think about the example here, we only have two-layer convolution. We only have a 6 parameter here. But if you're trying to use the dense layer, it will be 27, which are all the union times like 18 here. Which 27 by 18. I don't know how much would it be, like hundreds of weights. And last but not least, we also use the global average pooling, which will pulling to be one unit for one image. So for one image, maybe like 28 by 28, I will just pull in the most maximum, the average number, and get only one number out. So what does NIN block look like? So first, it's like convolution layers with kernel size, stride padding as usual. And it will follow by this one by one convolutional layers for 2 layers. So this one by one convolutional layers has one threading, but no padding. And it will share the same output for output channel as a fourth layer, so the channel size won't change. And as I said there, it's like act as the same as a dense layer. It's like 2 dense layers here, but with less parameters. So for one by one convolutional layers, how does it reduce the weight? You can see previously it's NH times NW times CI's input, and weight is kernel output times with the kernel weights. As what I just explained here, it like the one by one convolutional layers, it doesn't recognize the spatial patterns, but it just changes the channel size from the input to output, and will act as a dense layer with less weight. So the last layer for the NIN network. So NIN network is like a bunch of NIN blocks stacked together, plus this last layer of global average pooling. As what I just explained, the global average pooling for each channel is trying to extract just one element. So like the main element for that specific channel. But remember, we can have like maybe 1,000 channel. And even though we only extract one element per each channel, we still have 1,000 left. So as a summary, after the first 3 layers, we also have a NIN, which is using one by one convolutional layers to reduce the parameter, and also use the global average pooling instead of the dense layer in the end. Any questions? Okay. Next is Inception. Anyone watched Inception before? Yes? Yeah. This used to be my favorite movie. I like it a lot. And the Inception actually is got out of the same year as a movie. That's why they call it Inception. So what does it do? We have already talked about this 4 different architecture: the DayNet, AlexNet, VGG, NIN. You might wondering what architecture should I choose? And we have this kind of one by one convolution, a 1 by kernel, 3 by 3 kernel, 5 by 5 kernel, and max pooling, average pooling, this 1 by 1 convolutional. So there are a bunch of like model architecture available there, but what should we choose? And probably we can choose all of them. That's the base idea for Inception. We have this 4 paths, and each path is how like a 1 by 1 convolution, or 3 by 3 convolution, or 5 by 5 convolution, or you can just use the max pooling layer here. So it uses like different spatial size of convolutional filter kernel here. What you do is like you have this input. You have this input similarly for different paths. And for the first 3 paths, you have this 1 by 1 convolutional on the kernel to change the size of the kernel. So your input size will be different for this like 3 by 3, 5 by 5 kernel. And then, but for the last layer, it just apply a 3 by 3 max pooling, which is trying to extract the spatial information. And in the end, each of the architecture, each of the layer has their output weights. What we do, we concat everything together, and this concat layer will have the exactly same shape, same height, and same width as the input. So this is called the Inception block, which is pretty amazing, like your Inception in 4 paths of dreams. Besides, what does it do? It's like reduce the channel size. Why it reduce it? I will explain a little bit later. But it also allocate different capacity, because now we are not only using 1x1 or 5x5. We're using everything to trying to capture the best features. So the GoogleNet. The main part of GoogleNet is those, you see this smaller inception here. There are like 2 inception here in the stage 3, and 5 inception here in stage 4, and 2 inception here in stage 5. So that's how the GoogleNet mainly infrastructure. So GoogleNet contains 5 stages with this 9 inception block, and we are using the max pooling layers after each of the inception. You can see like max pooling 3x3 here. And we're also using the global average pooling in the end, like the AIN. And you can see the first part, which is stage 1, 2, they're identical to Alexander and DayNet. Similar local feature, like the primary feature extraction as Alexander and DayNet. So stage 1, 2, similar to Alexander and DayNet. It's just we use a smaller kernel size because now we have more layer, and we have the similar, exactly same actually input size, but with deeper layer, we don't need to reduce that too quick. We just need to reduce that step by step, maybe using a smaller convolution layers. But previously, Alexander using 11x11, and now we are using 7x7. And step 3, it says 2 inception block that we have the input, which like 192 by 28 by 28, and we condense it to 256, and we have them as input. We allocate them differently. You can see even though they look different to you, but the number for each of the paths are different. For example, we are assigning the 62 unit to be the convolutional kernel, 1x1 convolutional kernel, and we apply this 128. So which means for the output, 256 value, 128 are from this 3x3's output. But you can see from the later case, we are focusing more on this 3x3, which we assign this 192 unit here. But also the output for them also grows, which increase output channel. Any questions? Great. So stage 4 and 5, which we increase our output kernel a bit more. As you can see, from the stage 3, we have this 480 kernel, 80 channel, sorry. And then it's like 512 until the end. We have 800-ish channel. Because each channel is learn different thing. That's why we increase them regularly. And in the end, we have this 1,000-ish dimensional feature output layers, which means from this 1,000-ish output channel. And we do the global average pooling for each of the channel. We just put 1 unit, and that's why it's end up with 1,024 dimensional features. So, and GoogleNet gave us a really great result. And in this model Zeus performance chip, you can see that for this accuracy about like 0.78, I think, it can predict almost 900 examples per second. So pretty amazing. Any question? Okay, let's switch gear. Okay, great. Finally got a question.
What's the idea behind the size of each layer? Like why is 1024, why the other layer is 800 something?
Okay, so if I'm getting it right, the question is that why we're trying to gradually increase the layer.
Why is that particular number also?
Oh, why is a particular number? That is because we usually choose this number like 1024 to be some power of 2. So because like in the GPU, if you want to maximize the utilities, it should be like either 2 to the power of 4, for example, is 16, 2 to the power of 5 is 32. That we set as batch size. Like we can use all the GPU there because it's like binary, like 0 and 1, right? So it's like 2 to the power of something. And that's why we choose like 2 to the power of 10, which is 1022. That's a good question. I'm not quite sure why the researchers set him up this way. I believe when they do the experiment, probably this neural network works the best. Maybe, I guess, when they set up previously, it's like this number is either 512 or 1022. But they're trying to do an average over that, or these two number, and it worked best, and they just keep this there. Just have parameter tuning. Yeah, exactly. But you want to like grow it gradually. You don't want to grow it really fast. Yeah.
For the inception nets, I'm not quite sure why do we have like 2 softmax layers. It seems like we haven't have just only softmax at the end, not this one.
Okay.
The one in the like its very first page. I'm not quite sure
You mean the AlexNet?
No, the inception one.
Oh, you mean the 2 1 by 1? Is this one the block?
This one.
Okay, I saw it. So okay, this one. Yeah. So what's the question?
Yeah, because I just saw it seemed like we have like 2 softmax output.
Two
Right?
something? Oh,
The
yeah.
orange one. So I'm not
Yeah.
quite sure why do we have like
Yeah.
softmax at the intermediate
So,
one.
Yeah, that's a really good question. So you will see that there are like some yellow box here that we're trying to predict in the middle of the model.
Yeah.
So we want to evaluate whether the more deeper the model will be better, right? So if it works in the middle, it has a similar accuracy as we have the more deeper layers, then why we need time to train the like later layers, right? So we kind of gradually still testing and to see whether the accuracy or the loss is still dropping or the accuracy still increase. Yeah, that's a good question.
So
Yes, please.
this one is just to like debugging, right? Or
Not only for debugging, even if your model works very well, we don't want some of the weight to be idle, right? Say, like in the middle, if you predict the same result as in the last layer, then why we still need to keep those layers after the middle of it? So even if your model is quite well, you can still test it in the middle of it to try to be aware that whether the other part is still working.
thank you.
This question back then.
Hello. May I ask about the Google Net? I'm just wondering that from yesterday you talk about when dense layer we try to avoid the bottleneck architecture, right? But here in like Google Net, it seems like as we use convolutional layer, we can increase so the dimension can be increased, right? But I'm just wondering that if we try increasing the filter of the convolutional layers, and then does it redundant the number of, because when I see the number in the architecture, it seems like from the first layer we have only 512, but the deeper layers go, you have more increase. It seems like you start from really low number of filters, but then you just increase like the information from the layers.
Yeah. That's a good question. So what we do is like we try to increase the channel rather than increase the picture itself. So originally, probably it only have like, for example, like now we only have 192 channel, but different channel can learn different thing. Like different filter, different kernel can learn like the edge, like horizontally, like vertically, etc. So it's just like so many channel there, and the more channel we have, the more feature we can extract. And as for the bottleneck thing that you were talking about, it's, I believe I can draw it there somewhere. So the thing we should be, the thing we should be avoid is that like you have your input here, and then you have a bunch of neural network. So you don't want your neural network to like this. So you don't want your neural network to look like this, which you have your input, you have this like bottleneck, or maybe you enlarge it to even larger, and you decrease it to like your class number, which is like, for example, 10 here. You don't want that. You don't want like in the first few layers, you don't want to decrease that. What you can do is like you can definitely do some exploration with your current features. So you can enlarge that a little bit, maybe a little bit more, and you get this shape. And in the end, you decrease it to 10. So this like, there's like no bottleneck like this part here. Yeah, so try to avoid this. Since like in the earliest layers, we're trying to catch the local features which are pretty useful. We don't want to lose any information. Yeah. I will just cut it right off it. Okay, any other question? And I will resume. So let's switch gear a little bit. Let's talk about some mathematics. Hopefully not that tired anymore. So think about the Google Net, which is pretty long, from your input data to your output loss. I don't know where the trigger, but seems it will have some shift from this input to the output. And the loss we calculate is always happening at the last layer when we compare our prediction to the truth. So every time we backpropagate that arrow to the last few layers, it will learn pretty quick how to adjust the weights. But on the other hand, the data is inserted at the bottom from the front layers. So the last layer need to take a really long time to learn these features. So it's like really slow convergence. And just like the covariant shift, but not exactly the covariant shift. And what we want to do, can we avoid this kind of change of last layer while we're still learning during the first layers? So the answer is yes. What we can do is we apply this called batch normalization algorithm. So what you do, we fix the mean and variance within a batch. So you have this mean over this batch B, and you have all of the values summed together and divided by the norm of B, which is the size of this batch. And you also calculate the the variance of this batch, and you plus like epsilon to maintain the numerical stabilities. And we also adjusted a little bit with our artificially mean and variance to keep it consistent. So what batch norm really do here? It doesn't really reduce the covariant shift problem, but it will trying to add some regularization as same as the dropout. So what I do is like it has the empirical mean here and empirical standard deviation. Why we call it empirical? Because we're just calculating the mean within this batch. So that's like kind of experimental. And since each batch is changed every time, and this kind of mean and the standard deviation will be different. And so that's why we kind of apply this gamma and beta here to be this new x I plus 1. But that is kind of some noise injections to it that we regulate it and re-inject it back to it. And same as before, since Dropout also doing the regularization, then we don't need to apply both of them at the same time. And another trick is that the ideal mini batch here is 2 to the power of, I believe it's 8 here. And yeah, so this is a random offset and random scale. So how do you use it? Pretty simple. Just call the Gluon package.n.batch norm, and you can do the batch normalization for each layers. And for the dense layer, which is a MLP, we just use one normalization for each layer. But for the convolutional, we apply one normalization per each channel. So if you have 1,000 channel, you need to apply batch normalization 1,000 times for each of them. So it's effective as regularization and optimal batch size. Before ResNet, any questions? Okay, pretty interesting ResNet neural network. This is one of my best things because it's kind of not randomly designed by some engineers' intuitions. Like you just watch the Inception movies and then you go back home and design this Inception neural network. So the ResNet neural network is really based on math, based on the Tyler approximation theory. So when we look at these two pictures, one of them seems to be a little bit diverged from its central. So what are we going to do when we're trying to find this, optimize this f star f? We're trying to minimize the loss over all the input value x and output value y, and all the f, which should be within this big F, which within this domain f function. So our optimized f should not be outside this like white, the biggest square or the contour here. Then every time we're trying to optimize it, we want to find f star be smaller within this big white contour. Rather than the left-hand side, even though it seems to be grew to the optimization, it's kind of diverged to the right. Maybe it's not in the central and it's out of the domain of this big F. So we want to do something like the right-hand side, which is some nasty function that's within this big contour. And that's a basic idea for the ResNet. And the reason I love it is it's using even though the first order of Taylor explanations, what we want to do, since we don't want to diverge too much from the original x, how about we just learn it and also replace it back to the fx. So as you can see, compare from the left to right, we have the big square here, which is the normal convolution and weight layers. But we also have this another root on your right-hand side. We inject this x back to the fx and have the summation apply on the active function after that and put that to the next layer. So that's a basic idea for ResNet, residual network. So the ResNet in detail, what do people do to keep and preserve the original feature? They just use the one-by-one convolution. So the one-by-one convolution doesn't learn any spatial features. They just change the channel of them. So there are also many different flavors of ResNet. You can switch the order of them. You can do 3x3 first, then run batch norm and the ReLU. Probably you add a batch norm here, and you plug them together and assign a batch normalization. Or you can do ReLU first, and then the 3x3 convolution, and ReLU, batch norm, etc. So that's why when we tune this hyperparameter, we also tune this architecture. That's why the Auto-ML is pretty famous now, since like people don't need to sit there to tune it, to like change the sequence of those model layers. It's just like the model will tune itself. That's like why Auto-ML get famous. So if we put everything together, the ResNet is similarly as VGG or GoogleNet. They just stack those ResNet block together. So you can see here is a ResNet block. You have like 1x1 convolutional here. Here probably another one, and which we call the ResNet connection. It's added to each of the block, and we're also using the pooling and strat to reduce the dimension, because if it's coming too large, we don't want to keep too huge dimension. It will be computational expensive. And we also use the batch norm for the capacity. So let's see the result of the ResNet 152. By the way, it's 152 layers. It can train probably not that fast as before, but it has a definitely higher accuracy, above 0.8. And you can see this result in the Gluon CV model zoo. So just search for Gluon CV, it will just show here. Jupyter Notebooks. Okay. Before that, any questions? No? I think everyone is like good to go. Like we can all train the ResNet ourselves with high accuracy. Well, okay. So if no, then I will talk about more architectures. So I won't talk about them in detail, but just show you there are millions models out there after the ResNet, and you can learn from. There are different people have different idea, but probably only fit for the specific data sets, which means they probably be a little bit overfitting for that, but I will just show you their ideas. So the first is DenseNet. It's also some kind of Taylor approximation, but now we are doing a higher order. So remember, for the ResNet, we're only doing the first order Taylor explanations. We only plug the X back, but now, thing was that we plug the S2 back. So for each of the layer, we're trying to inject the previous learned features back to the current features. So we plus them together, we're trying to still keep them so we won't diverge too far from before. Now that's the basic idea. So as you can see here, we have like the Taylor series expectation. The original one is like x1 equals to x, and then x2 will equals to s, and f1 of x, which is like the summation of them. And then the next step we can be, there probably should be s3 here, sorry. And then it should be like a vector of x, f1x, and f2 over this previous x2. Yeah, so the idea is just like a Taylor explanation for a higher order. And another interesting net with an interesting name called squeeze and excite net, which means you're trying to squeeze it and trying to make it excited. And the kind of intuition here is that previously, when we calculate the weights for this channel, the channels, we think about them have a similar weights. So if we have 1,000 channels, we'll sum up them together, apply the mean for them. We don't really weight them. And what squeeze and ExcitNet is trying to learn is that it's trying to learn the different weights for different channels. So probably different channels learn different features, and maybe different feature has different importance. And that's the weight they're trying to learn. They're kind of adding some attention mechanism for each of the weights. And so it will learn the global weighting function per channel and allow a faster information to transfer. Since it has a weight, the larger weight it has per channel, probably the the quicker information can be transferred to the last layer. And another interesting layer called shuffle net. So remember the ResNextNet break the convolutional into channels. And each channel is learned by themselves. They don't really communicate with each other. But probably they can communicate with each other and learn more interesting features. So the shuffle net is trying to mix up those channels. And you can see there's like red channel, green channel, blue channel, and each one has their specific feature they learned. And they kind of mix up together randomly and group them together. As you can see on the right-hand side, you have those channel shuffled, which you have red, green, blue, and then you try to learn the new features from the other channels. Also pretty successful, interesting channel, but probably only applicable for the RGB image feature dataset. And fine-tuning. Before I talk about fine-tuning, any questions? Okay. So fine-tuning, it's a pretty important idea. It's not an architecture anymore. We are done with architecture. And what we're trying to do is that now we have so many architecture. Can we use something that other researchers have already trained and take it here, do some transfer learning on my own data set? So it's like maybe someone already trained a phenomenon models like ImageNet. And now I'm trying to classify dog and cat. Can we apply the similar model using the same architecture with a similar weight on my new data set? And can I still learn from it? And the answer is yes, but we need a little bit tricks. So now think about that. We have we know that everyone knows that labeling data is super expensive and tiring. We cannot spend our effort on this 1.2 million data set. So suppose we have this 50K data set, which are all cars we want to learn, whether it's a trunk, whether it's a car, whether it's a taxi, etc. And we have like 100 class. But it will be definitely pretty small compared with ImageNet classification. So what should I do? I can definitely reuse it with the neural architecture that ImageNet, the other researchers have, like the ResNet or DenseNet, GoogleNet, etc. So for all the architecture I just mentioned before, probably we can divide them to be two pieces. So for each architecture, we have the first piece, which we can call is like feature extractor. So what they do, they try to map raw pixel into some new features that can be linear separable, or it can be learned by the next convolutional neural network or dense layers. And another piece is this final output layers. It will be matched to your exactly output class. So for ImageNet, it will be 1,000 output class. So you have like a dense with 1,000. And for my dataset, probably I only have like dense with 100, since I only have 100 class. So which is like a linear classifier. So that's the basic two components for our neural network. And how should we use them? So the first way is that we can definitely just fix the lower layers, which are those feature extractors that we're trying to extract the lower features, because the lower features are always universal. Think about that. For eyes, like every animal, human has eyes, animals has eyes. Like as long as the eyes, we know that it's kind of animals, right? So it can point us, it's not a car anymore. It will be some kind of animals. And higher level features, as you can see on the upper right side, it's like it can recognize whether it's a dog, whether it's a human here, whether it's like, I believe it's like some kind of universe here. But upper features, it's trying to extract the universal object for it. So what we can do, we can just fix the bottom layer, which are trying to extract the universal local features in the lower level of layers, probably the L1 to maybe L minus like half of them. So this is one way. But remember, for fine tuning, we have different of classification. So we definitely do not want to keep the output layers. But probably we can keep the previous our layer 1 to layer L minus 1, as they already a good kernel there, already learn a lot of features. So probably if we do a little bit of fine tune using our new dataset, and probably they'll work. So what we are doing from the source model to the new target model. So on the left-hand side is a source model that will train on the ImageNet dataset. And you have this like pre-trained model. You grab it from either a Gluon CV model zoo, you grab it on like the other open source package. And we apply it on our target dataset on the right-hand side. So for each of the layer from 1 to L minus 1, we copy them. Just copy them, copy them, copy them. And then until the last layer, we don't copy it. We don't want it. We just random initialize with like maybe mean of 0 and standard deviation of 0.01 to initialize those weights, and we just learn it from scratch. So we learn it from our target dataset, from input, and we have this output with this 100 difference of cars. And we train it from scratch, and the last layer will learn, and it will have some gradient errors, and it will back propagate to tune the previous layers so that we just copied from the pre-trained one. So we'll kind of fine tune it. It won't be recognized, so like maybe the L-1 layers will recognize some human, recognize some animals, and it won't be that useful for the cars. So the neural network will just learn it by itself. Probably that's not useful. Maybe I will just get rid of this kernel, this channel, etc. Yeah, and the recipe for that, you train your target DNS as normal, but with the strong regularization using a smaller learning rate, because when you do fine tuning, it's already like training a neural network from the later stage, because you already have your weights building up there. That's why when you do the adjustment for the gradient, you need a smaller learning rate. You just need learn a little bit to adjust the fine tuning layers. And probably you want to train on a fewer epochs rather than set up 1,000 epochs here. And when you finish, you feel, oh my God, I'm diverged, which is not what you want. And another tip is that if the source dataset is much more complex than your current target dataset, then it's a good news for you, since it means that your source dataset has more feature, like the ImageNet dataset. It has 1,000 different class. It definitely has more features than the current dataset that I have. So which is a good prayer for me to learn, to fine tune. Yeah. Any question for the fine tuning? Yes, please.
I learned that when they fine-tune the networks, right, sometimes they freeze the network and unfreeze only the last one. But the other time, they may unfreeze like -1, -2, -3. Any criteria that you're going to suggest?
That's a good question. So the question is that, like, how many layers should we unfreeze? I guess when you start your model, probably you will just unfreeze a little bit, and you will see whether your model learn very much. Because there will be two problems. Either it's coming from the previous trained weights, like the previous layer, they like kind of diverge from your current data set. Like for example, if the original model is trained on some animals, and your new data set is trying to include animal but also human, so probably it will be diverged. It wants the human's features. And then you can release more layers if you feel it doesn't improve a lot, and gradually increase your learning rate. Yes, but that's a kind of experimental problem. It's hard to say how many layers should you release, but release gradually when you train and do smaller epochs to say. Because on the first part of epochs, it will definitely learn gradually, like much more than the later epochs. Yeah, exactly. So when you train each epoch, remember we point out those loss graph that it kind of like decrease every time, and that's the kind of thing that you want to monitor for each of the epochs, or maybe every 10 epochs or 100 epochs if it's like a small data set, it's like faster training. But you want to monitor yourself that it's like definitely decreasing every time you're trying to optimize something, or if it's not, if you see the loss increased, so probably the model is not learning, and then you can unfreeze some of the layer to like kind of fine tune a little bit earlier. Yes, good question. Any other question? Yes, please.
Yeah, I wanted to know that yeah, you want to like freeze the layer that contain a lot of shared features, right? What if that layer also contain like task-specific feature that you don't want to include? How do you segregate it?
So you mean, what if there are some useless feature that in the first few layers that are freezed, which are pretty useless for my model training?
So I'm saying that what if there are like some task-specific feature for the source task, instead of the target task that you don't want to learn, like, but you already kind of freeze it. How do you like segregate those features?
So usually when we freeze those features, they're kind of lower level feature. Like if you see the photo here, at the bottom side, they're like for, maybe it's not displayed that great here, but it's like all the lower features that either can be eye, can be a hand. So mostly, or for a car, it can be a door, or can be like any other basic feature that every car will have. So those features is the lower levels of the convolutional layers the kernel will learn. And when you freeze them, and it won't change anything, right? It's like, even though the ImageNet might learn some feature that you won't need it, but there will be some other features, some other weights that you want, right? But when you learn it in the later model, when you learn it with different weights, with different channel, and the channel will know, oh, the previous channel, it doesn't work. It doesn't really help me. So we'll just, when you do, especially when you do the dropout, it will just reduce it. It just won't learn from it. So maybe the weight for that is pretty small to learn that specific channel. Yeah. Yeah, that's a good question. Okay. So I believe we are done with all the slides. Congratulations. We're so quick. I was worried that I cannot finish it. But we're good on time. Nice. So I believe everyone is tired again. Do you want to watch another video? I have a bunch of interesting video. Or you want to go to the Jupyter notebook and run the code with me? Raise your hand if you want to watch the video. 1, 2, 3, 4, 5, 6. Okay, group of hands. Raise your hand if you want to run the code with me. Oh my god. That's sad. Okay, how about we watch the video first and then we can run the books. Sure, but it doesn't make sense, right? If I just show the result, because I already showed the result for all those models. What we want to know is like how do we implement it? Maybe I will. Oh yeah, that's a question. Because that's like the internal thing. I can only access myself. So it will be super slow, right? Let's try first.
หน้าตาเขาจะลองอะไรกัน
Yeah, because this is like internet. I probably need to my last big key. Yeah. Yeah, no worries. No worries. So shall we finish now or do you guys have plans after that? What that? Another session?
I'll close the session.
Okay. So yeah, probably. I think I'm good for now since like I want to show this deep research, but I don't think it will work. I will put in my laptop tomorrow and we'll see. Okay, guys, sorry about that. Since this video is only on my laptop and the other people cannot access it, so I will bring my own laptop so I can just directly connect this and you can show it. It's pretty cool. It's a deep research competition within Amazon, and it's kind of recording to showing how does I run coding, how does the competition go. So thank you for attending, sitting here until 6 now, almost 6 now. But have a good day, and I will see you tomorrow. Thank you.